Hi there, I'm Deep Dylan. Welcome to your AI Injection, the podcast where we discuss state-of-the-art techniques in artificial intelligence with a focus on how these capabilities are used to transform organizations, making them more efficient, impactful, and successful. Welcome back to your AI Injection. This week, we'll be discussing the use of AI in chemical engineering and industrial processes with Dr. Sebastian Werner. Sebastian has a doctorate degree in chemical engineering and currently works as an AI Evangelist at Dataiku, a data science and machine learning platform that designs, deploys, and manages AI applications. Thanks a ton for coming on. Maybe get us started about how did you get into chemical engineering and how did you get into AI and machine learning? Let's start there.
That's a super interesting question. So I started thinking about chemical engineering because I couldn't really decide what to do after high school. And I was interested in let's call it things that are between the worlds. Not really, I couldn't decide on mechanical engineering, not really on chemistry. And I was always interested in modeling. And that's also modeling real processes for, let's say, some benefit. That was something that really got me. And one part of there is sustainability, because efficiency is one thing that really drives chemical engineers. So that I would say is the motivator that brought me into chemical engineering.
How does a high school kid have a vision of that?
So that goes back to let's say to the old times, to the 90s. So I saw this. So back then, a guy in Switzerland called Grätzel came up with this Grätzel cell, the photovoltaic cell to artificial photosynthesis and all that stuff. And it was super fascinated by that.
Okay.
I was say, wouldn't it be cool to build in the end this idea of, let's say, painting your wall green, spraying some water on it, and down drip some, let's say, sugar or in the best case alcohol? Wouldn't that be cool to do that instead of I don't know, making in big factories? That was the idea. And that was kind of bringing me.
Wait, you got rooms, you got paint, you want to drip sugar down, just because the effect would look cool? What's the sugar's role? Are you trying to?
So let's say photosynthesis. We have CO2 in the air.
Yeah.
And we can use sunlight, photosynthesis in the first case. So just imagine we do artificial photosynthesis. So we manage to put photosynthesis as kind of, let's say, just a paint on the wall, and then just add water to it, similar to a tree, and use that in order to produce sugars for us. And then add a second step in that process, fermentation, to take that sugar right away and make alcohol.
So there we go. Now we get to the high school kid. So somehow that turned into a sort of desire to kind of maybe understand how to model these more physical chemical reaction processes, and that took you into that world.
Yeah, absolutely. And to say it more precisely, in high school chemistry, we went to a trade fair called Achema in Frankfurt, and I saw these giant vessels, these giant factories, because we have no scale about it, how big such a factory is. And I was cool. Then there must be a way to learn how to do that. And I liked chemistry, I liked physics, and so I liked engineering. And so I was hey.
I mean, that makes a lot of sense. I always felt terrible when my kids were younger, take your daughter to work day or something. And, the most exciting thing for a 7-year-old is a bowl of licorice or something. It's just a bunch of computers in a loft somewhere with a bunch of geeks staring at them. And I always felt jealous because when I grew up, my dad had this huge research lab with all kinds of contraptions. And there's just something about seeing these larger systems that's way more interesting than seeing them in a model in your computer or something.
And I mean, as a kid, you ask yourself, how do these stripes get into my toothpaste? And then you ask the second question.
There you go.
How on earth do you manufacture toothpaste? It's how it's made. And the thing is, all behind that is always chemical engineering or process engineering, because it's about
scale,
getting a raw material into something you can use as a human at scale, because these factories are ginormous.
And you can't sell toothpaste for $50 a tube, so you have to figure that out. Yeah. So from chemical engineering, somehow you wound up in machine learning and AI. What was that? What led you there?
Yeah, in university times, when I studied chemical engineering, one important part is to understand the chemistry and physics behind the processes. And I got somehow attracted by the thing that calls of most people, meaning thermodynamics, like understanding for like if you have no idea what's that about, it's about like, hey, what happens if you mix certain things? Let's say, take the practical example of water and ethanol. You mix that together and you heat it up. So distillation, that's a very practical thing. But like the theory behind it really fascinated me. And that got me into the point of, let's say, modeling, so-called flow sheet modeling, when you try to end-to-end model a chemical process. And that's, in the end, you could say, how I ended up at machine learning, because there's a lot of these same techniques behind it that we nowadays use for machine learning and later on for AI.
Yeah, so in the traditional chemical engineering pre-AI machine learning world, walk us through what things were like then, and then maybe what is in an undergrad learning now that's kind of incorporating these statistical processes that help model some of the uncertainty that that maybe the physics and chemical modeling doesn't get to directly.
That's an excellent question. It's to a certain extent a little bit like chicken and egg. When you want to model whatever process you have, you can either start with the data. Let's say that's where machine learning AI is in. You have observations, or vice versa. You can start off with a model first and try to adapt that to a certain reality. It's like the chicken and egg problems. Think about physics. There's a guy like Mr. Newton. He sits under a tree. He sees an apple falling. He does an observation. He says, there must be a relationship behind it. Then coming up with a fundamental relationship. In the other way, you could say, hey, Mr. Higgs came up with the observation, hey, Higgs boson, that must be there. So we built a super complex LHC collider and made the observations afterwards in order to validate the model and fit the data to it.
Yeah, makes a ton of sense.
Super high level view in this.
Yeah, no, I mean, like, like a modern Newton sitting under a tree. Now you've got a video camera. Maybe you do some semantic segmentation. You track the apple as it falls. You measure the acceleration. Maybe you weigh it. Maybe you measure the force. You put it all together, and then you wind up with F equal, like your actual.
And that's equation. The super rigorous points that you said, like all these details. It was like the first part, like chicken and egg. Where do you start? So going to the modeling of a process, the same is true like when you model, let's say, a chemical process. You can start up building it up from the fundamentals, these little bits and pieces, starting from like Newton's gravity law to all these other pieces. You can put them on top of each other and build so-called first principle model. That's what you learn in university, flow sheet modeling. You learn all these relationships, physical, chemical ones, like continuity laws and whatsoever. That's the first thing you can do. And you build that for, let's say, a factory. And the one thing you find out is, it doesn't really fit. So what you need to do is you need to then take observations from that factory, if it already exists, and you need to fit the data to the model. So you adjust some parameters. And that's already, you could argue, machine learning, because you do statistical fitting of the parameters.
Yeah, walk us through, like, where are some of the points in this chemical plant where reality butts up against the equations that you've got that make everything, because those of us who've studied this sort of thing, you understand that the equations kind of have a whole bunch of parameters and there's a lot of approximations built in, but in reality, like, what are we talking about? Like, pressure variations, temperature variations that are just sort of shifting throughout the day that maybe don't get reflected.
It's almost at all levels. So certain things we understand very, very well. Let's say thermal conductivity, we understand fairly well if we have pure substances on both sides, meaning there's pure water on one side, and there's like pure water on the other side, and there's just, let's say, 2 inches of metal in between. You say on one hand, it's like warm water on one side and cold water on the other side, and you say, okay, explain to me and build a model for, let's say, how will energy flow from one side to the other, and what temperature will I have on the other side after 2 hours? That's, let's say, fairly well understood. That's complicated as soon as, let's say, effects that are, let's say, slightly chaotic come into play. Let's say boiling
Kool-Aid mixed with granola, maybe. Like, it's you have
like first thing is, let's say we have boiling water. Are you really sure that you understand what happens when the bubbles form on the surface? That's not completely analytically understood. In the same way, if you now, instead of just pure water, you take a mix of, let's say, water with a little bit of, I don't know, salt, or a little bit of ethanol, it already gets more complicated. So that's the starting point for where it gets a little bit more fuzzy. So now let's go to the factory. Assume you have a heat exchanger at the large scale, and you want to cool down a mixture of, let's say, whatever material you're dealing with. The heat exchanger will not be the same when you buy it than 3 months later or 2 years later, because there will be something called fouling, meaning there will be some material built up, and for sure, the thermal conductivity will change over time. Do you really understand what's going on there? Not so sure. And here's exactly where these points come into play. At all these levels, certain things come in that we don't understand that well.
Makes sense. So walk us through, like, maybe we should take a scenario. Pick something that you either worked on or that you can think of that's an interesting chemical transformation or process that you're trying to engineer, and walk us through, like, where is AI being applied in a particular scenario?
Let's before we start going into AI, I think staying with that example with the process is a good one, because especially that heat exchanger we just talked about. Now just imagine you have these observations from this heat exchanger where you have on one side a material you want to cool down, and you have cooling water coming from reservoir. And what you have is the temperature of the to-be-cooled material of both sides, and so on. In a simple way, you could just say, hey, I have these observations on all sides, and I know how much cooling water I'm putting in.
And you probably have some inputs, like you've got the thermostat that you can turn up or down.
Yep.
Maybe you have pressure, I don't know.
And now let's just say you want to make sure with this heat exchanger that whatever fluid you want to cool down has a certain temperature on the outlet. And you see, hey, over time, I have to open my valve for the cooling material more and more and more and more to reach this temperature. So you don't have a model about this, about the fouling that is happening there. However, what you can do at scale with artificial intelligence is for every single one of your heat exchangers, take exactly these data pairs and let AI for you figure out, that's a predictive maintenance.
How much to turn the knob one way or the other. Yeah.
When you need, not only that, how much to turn the knob, because there's control software for that, but when to call a cleaning crew in to clean this heat exchanger and get all the fouling stuff out. Because if you're in a situation where like you cannot open your valve anymore, then you have a problem in your process.
I missed something. So you've got these big vats of the thing that you're trying to cool, and then the thing that's doing the cooling. And what's the fouling that's happening? Like something goes inside the...
Oh, sorry, I have to go back a step. So the cooling water is never clean. It always has some stuff floating in it. And whenever there's something floating in it, bacteria and like whatever you can come up with, it will happen to build up in the heat exchanger. Heat exchanger,
it'll start to grow if it's bacteria,
for example. Yeah, it starts to grow and so on. You can try stopping it, and also there's some rust that might build up and so on. No matter what, this effect fouling is in there, you will not get rid of it. The thing is, taking a heat exchanger out is costly, so you don't want to do it too early. But if it doesn't do its job anymore, it can be a problem for the process that you're operating it in with. And so predictive maintenance of something like this can save a ton of energy. And to do this analytically with a classical model is not always easy, because there are so many unknowns. You don't know how fast will the stuff grow on there, how fast will it rust, all of these things you don't know. However, if you have the observations, that's exactly where AI can help you to figure out, hey, by the way, at about this time, likely it will reach a critical level. You probably should schedule it.
And that gives you a chance to get your resources lined up for that day.
And with that example, we pretty much explained the entire use case of predictive maintenance, which is one of the key use cases of artificial intelligence, not just in chemicals, but also in entire manufacturing. Just observe what you see. You have AI figure out a certain trend by means of a regression model, specify a critical limit, and use that in order to alert you when a problem comes up.
Yeah, and the key is that it's something that's not straightforwardly modelable, or at least with a high level of certainty. Like in the case of the bacteria, who knows what's floating around in the air at that particular plant, or you know, the state of the metals. And
just imagine you directly use water from the river, right? There's a lot of stuff floating in that. And that's in many cases because it's costly, cooling water. You take water from the river, and exactly this is what happens. There's all kinds of stuff in there.
You're listening to your AI Injection, brought to you by Xionyx.com. That's XYONIX.com. Check out our website for more content, or if you need help injecting AI into your organization.
So what did folks do before, pre-machine learning? Were they using more basic statistical methods to do this, or?
I would say yes, but in many cases, it's also, do you really have the time to have an expert engineer sit down to build 500 models for your 500 heat exchangers in your plant? So what you would do is you probably have a schedule, or you just simply have an alarm in this case that just says, hey, if the output temperature here becomes critical, this is when we just do that. And of course, this is the most simplest case where you could do AI at scale in the chemical industry or the process industry. But it's a starting point to like see what is the gap that we can overcome. Whenever we have phenomena we don't really understand that well, use the observations of the systems that we have in order to bring our understanding of the system to the next level.
So taking this example that you've got here, I mean, I'm just guessing that you must have some modeling software that lets you run through some scenarios like this, where you can play between the physical world and the machine learning world. So in the physical world, you can set up your exchanger scenario, you can set up your materials on both sides. Maybe you can even like introduce some bacteria or some stuff and then have something like mess around with it. And then you can try out your observational models. Like, how do you assess efficacy on something like this that has such a long potential?
So that's an excellent question. The first point I would say or argue is that I believe pretty much everything we see in the process engineering space, you could solve by traditional first principle modeling methods in the software that is available out there. They have been around for a long time. And here's the thing, given enough time and manpower, and meaning resources of experts to model that, you can do it. However, there's always the question of like, how much do you have to invest versus like, what's the payback for this thing point?
Yeah, I mean, I guess I was getting more at like the question of not so much like replace potentially the machine learning solution with the physical solution, but how do you test the machine learning solution when you've got this big giant vat and you've got a theory of a model? You put it into place. Like, do you wait months and months to see if you actually called predictive maintenance, like you predicted your maintenance at the right time, or do you take it all and maybe sort of try, or maybe do both? Maybe you trial it out against different physical scenarios.
All of the above is done. So I've seen people doing just like running it and seeing if it works. I've seen people benchmarking a machine learning model against a first principle model and vice versa. I've seen first principle models being benchmarked against reality and the same reality concurrently also being tested against a machine learning model. All of that is possible. And the thing that you mentioned that is actually the gist of that is the problem is the process we're dealing with are slow. When they're slow processes, it's in some cases very hard to also see the impact of certain decisions or certain things that are happening because you have so many influencing factors.
Now I'm kind of curious, like when you build such a model for a particular process, like what are the maybe open available resources look like for chemical engineering AI people?
Super interesting question. I would for 1 second take a step back and to say, hey, what challenges are we dealing with in most cases?
Yeah, that's probably
most challenges we're dealing with are regression problems, meaning problems where we want to forecast a certain property or dealing with a series of numbers. And most importantly, we are dealing with time series, meaning effects like or measurements or observations based over time where the context of what previously happened really matters. And now, like going back to the AI and machine learning world, when you look at literature, I don't have the exact number, but like my impression is the vast majority is focusing on classification.
Yeah,
one
sure.
on the other,
Yeah,
and very few of them are actually regression techniques. And out of the regression techniques, even fewer of those focus on time series problems. There's a couple of things that happening there, but it's like, I would say not as far as like some of the other fields have gone in the past couple of years.
Yeah, however, I mean, just quickly, I just want to clarify for everyone. So like when we talk about a regression problem, we're talking about taking, a machine and trying to predict a particular value. So that might be, for example, like, Zillow or Redfin predicting the actual value that your house is worth, as opposed to classification where we're just trying to predict a category. Like, is this things spam or not spam. So go ahead.
And of course, and what's definitely true is you can take almost any regression problem and discretize it into a classification problem.
Yes.
That is definitely true. However, as soon as you add this like time context, meaning whatever you're observing is very much dependent on what you previously observed, in that case, it becomes very, very difficult to do that transfer. And that's one of these challenges. And we're dealing with real systems, meaning when you observe a certain value, it's not necessarily clear from the observations how you got to the state that the system is in that produced the certain value. Whereas like for forecasting, like looking in the future, this part really, really matters. And that's where like the challenges with machine learning and AI in that space come into play.
To your knowledge, is there any transfer learning? Like, like we think of AlexNet for imagery, and for NLP, we've got all of the embeddings that are trained on like really common large corporate. Is there some kind of analogy in your kind of process world that would be appropriate?
I've seen a couple of papers on transfer learning on time series. That's the first part. I've seen a couple of people that have worked with time series and used, let's say, established techniques from statistical learning like ARIMA and so on, and enhanced them with effects from neural networks. What all of these approaches are missing so far is being able to, let's say, incorporate like detailed feature engineering and so on, because like there's been a lot of like development going on, but it's like at a very more early or like infancy state compared to what we see in other domains. Because the complication is it's not just that we have, let's say with a classification, we have a certain value and we want to classify it. It's always this history, this the time domain matters.
Yeah, I mean, I'm just kind of, I'm almost imagining like, so you've got this time series that generate, let's take your heat exchanger template, right? So you can model that out. You can have this kind of standard heat exchanger template. My guess is there's like a standard set of variables like temperature and pressure, and et cetera. The question I would ask is like, if I saw like a million or thousands of different heat exchanger problems, and I'm looking at that maybe multivariate signal, are there properties within that signal that are common to this problem class in general? If so, it feels to me like you could bootstrap a network that learns the general gist of heat exchanger stuff and now go take it and apply it to your particular problem.
Absolutely. Totally true. The challenge is not there. The challenge is to get to the state that you get the data into such a model, get it out of, let's say, from the sensor that is out in the field, and plug it into a framework that it can actually reach there. I know there's some research in the direction of like usage of neural networks and so on for exactly these problems. But as I said, it's in an early state. For the easy cases like that, it's completely straightforward. For the more complex ones, or the more complex so-called unit operations, meaning heat exchanger as a unit operation, like for the more complex unit operations, it's not so simple anymore.
I didn't quite follow your sensor argument. So you're saying like, is there something about the signal in the sensor that's different than what we can model or something?
Let's take a step back. In order for your machine learning model to work, you need data and observations, right?
Yes.
So let's now step that aside for a second. So now let's go to the reality of the factory world. You now have a sensor that is sitting on a heat exchanger. The measurements that you take from there have to come to an infrastructure where you can run your model that we just said. And so these sensors are in so-called operational technology. They're embedded in so-called process control systems. And so getting them out from there, that is where like, I would call it, that's the abyss that is in between, or let's say the chasm that is in between, connecting these two worlds. Because the chemical industry traditionally doesn't do much in the cloud. They don't do much.
Oh, so you're talking about just the semantics or the act of getting these signals.
Absolutely. And then to go to an industry where the operational technology runs on a process control system from one of the major vendors that in some cases doesn't have an infrastructure that records all these measurements over time, which is the basis for all machine learning. Step one. Step two, if you have such a recording system, a so-called historian, then the question is, how do you get the data from this historian, number one time as a dump to a data scientist that would build such a model, or in an operational setup, how would you continuously feed this data into a machine learning infrastructure in a world where all of these, let's say the data scientists and all the computation infrastructure is hosted by IT, information technology, not operational technology. And then the next thing is the OT things are in many cases not running on open protocols. They're using proprietary interfaces. And so that's where the challenge becomes into, let's say, data accessibility and getting the actual data.
This makes sense to me, right? Because I mean, I come largely from the software world. In the software world, most companies are totally instrumented at this point because your sensors are basically other pieces of software. Who do you hire? Software engineers. They know how to like take their own data and shove it somewhere. And therefore you wind up with, all of the data kind of being centralized, typically in warehouses or, or lakes or something. And then you can start to like manipulate it. But in the industrial world, it's more complex because you have legacy physical things like distributed geographically oftentimes. Each of those things hasn't necessarily been Wi-Fi enabled with like data gathering that automatically lets you centralize it and get it up into the cloud.
And I would even say, take banks. Banks were the earliest ones that did digitalization like 50, 60 years ago with their mainframes and so on.
Yeah.
Still those ones that don't have they don't have like physical assets out there, they have the issue integrating these legacy assets into data lakes and so on. And now imagine you have a factory, you invested in some cases hundreds of millions or even billions of US dollars into building such a factory. You put all the process control systems in. Now the thing is, you will not take a lot of money in your hand just to upgrade them. So accessibility of these super heterogeneous systems, meaning they are all different. They're all confectioned to get them into one platform is a huge challenge.
So are you seeing a kind of huge movement as a part of, I don't know, we hear about it as the Internet of Things, but are like sensor manufacturers, for example, making Wi-Fi enabled or Bluetooth access, centralizing componentry to like get this stuff digitized or?
That view in many cases, I think, too easy, because in an environment where you handle explosives, you will not put in a Bluetooth or Wi-Fi sensor, right? So this is where the problem basically starts in this case. And also, yes, they are offering systems to like put that to the next century, but it starts with the fact that if you replace a process control system, you in many cases have a 5 to 6 digit numbers to update them because they are process critical systems. And to, let's say, piggyback a new sensor in will not solve your issue. It's not like the 50 euro sensor that you can plug in somewhere because it has to be hardened, has all the certifications for safety and so on, which makes the entry barrier for this like industrial Internet of Things a lot higher. So what's happening on the other side is that vendors are going ahead and building opportunities so you can use the existing legacy systems and enable them to, let's say, stream out their sensor data by means of MQTT. Let's say that's another example. So you retrofit existing systems to be able to send out their data, but that's also a huge effort.
And is that like somebody makes a little thing with a camera that points at a dial and figures out what the dial says?
Oh my God, no. Just imagine you have a process control system, meaning, let's say companies like Siemens or Honeywell make those, and you have 50,000 sensors and control circuits in a factory. You will not replace that right away. However, you already have the sensor readings, you have all the data there. The issue is you need to somehow interface with that process control system and get the data out in a secure way. And that's basically step one. There's an interface called OPC, Open Process Control, that exists and so on. But again, it has to fit in the industrial certification standard. So there's a lot of software companies now that make middleware to retrofit old industrial assets in order to enable getting the data out.
So why did that data wind up centralized in that plant in the first place? Is that because there were human operators or something that needed it?
So again, take a step back. How do you operate, let's say, a refinery or a chemical factory? And it's not that there's millions of people running around and turning knobs. No, they sit in the control room, and that was digitized or digitalized in the, let's say, 70s and 80s. So you have central control rooms with huge big screens. And what you do is basically you sit on your terminal and you type in a certain number, and a control circuit out in the field makes sure that the valve is opened or closed. So the data is technically already there, and you see the current sensor readings on your screen already.
So yeah, just to kind of make sure I got that right. So the vision I had originally is like, you've got all these sensors, go straight to the sensors, get the data. You're like, no, don't need to do that, because we already had a reason to centralize them, because we had these humans who were operating these plants. So whatever was
humans, it's not just humans. They're like control
or other systems.
out there.
Yeah.
So, and that's
okay.
the other thing, that there's already an entire field of experts, like process control experts, like in electrical engineering, that figured out rigorous models in order to automate certain of these parts already. And that means the sensor readings are already there. However, you have to get them out. And this entire first part is like the domain of operational technology.
So would you say maybe, I don't know, the 80% of the industry is in that stage, trying to get those centralized operator data up into the cloud where they can manipulate it? Or do you feel like that already happened largely?
That's a very hard question to say. I think that very much depends on the region, on like which industry, like specific industry you're in. I feel like in some cases, the thing is, why would you put it in the cloud? Or like, why would you put it somewhere that needs to be a pain? And if you're with the operating method that you have right now, you're pretty happy and you have like huge margins right now, why would you go ahead? Like, if there's no pain, there's not much happening. In some other fields, people have basically made this push. In the first case, to say, hey, it's not just nice that we have the data in one place for the operators. Why don't we store that data to be able to do analysis later on? That is the motivation to make a so-called historian, where you save all your sensor readings like every minute or so on, so you can graph it out and do some analysis. This is where like I would feel like most major companies are in. The next state is from that you are able to use that data in order to fit your models. This is where I would say a good number of the larger companies are in. Again, and then they're using the traditional first principle of flow sheet modeling tools in order to use that data.
That makes sense. So you've got this team of, I don't know, maybe industrial engineers or other engineers that or data scientists that are trying to find efficiencies in the process. And the first primary directive is to drive the plant. But within that, there's like all kinds of data being shot off that, where we can learn quite a bit. So that ends up being the forcing function for the centralization of the data.
Yeah, or in general, do you want to have people run around in the factory turning knobs? I don't think that's very efficient, right? So the first case was, let's say, a central control room was just like, you need, I don't know, 5 people to operate a $500 million asset, something like this, instead of like having 50 or so that are running around. So it's a cost factor in terms of efficiency.
Not to mention potential errors, I would imagine, with humans running things.
And now we're coming to the point why it's so complicated also to use artificial intelligence, machine learning in there. Because now suddenly, if you have an algorithm in there, you need to be as good and as adaptive and as secure and like safe in operating this compared to human, which means the level of certification you need to get for a certain algorithm to be approved to be run automatically, that's pretty high. Because let's be honest, a machine learning algorithm or AI, they don't care if they make a mistake. However, the people living around your factory very much care if the algorithm makes a mistake.
Perhaps you're not sure whether AI can really transform your business. Maybe you don't know what it means to inject AI into your business. Maybe you need some help actually building models. Check us out at xionyx.com. That's XYONIX.com. Maybe we can help.
So does the evolution look something like what we see with self-driving cars? Like self-driving cars, you've got, or if you go back a little bit, it starts to be suggestive. So you've got the operator still, but you're trying to like identify the guardrails, like, hey, you're about to go off a bridge, or, and you try to be suggestive. They start using that suggestions, and we're not yet taking their hands off the wheel.
So you could call that's an open loop system where you basically give a recommendation and someone looks at the recommendation and says, yep, makes sense, I'll act on this.
Yeah.
Whereas like a closed loop system would mean the AI is really in control, or machine learning is really in control. That you see in very limited cases, because coming back to our heat exchanger, for a simple heat exchanger, you could probably do that. However, if you take an entire factory, the level of, let's say, certainty you need to do that, and the level of checks you need to do becomes so big that the investment in that is probably higher than just having an open loop system and say, hey, by the way, I think this is what you should do, and have someone validate it.
Yeah, it makes sense. I mean, it's also like, even if you feel like your machine learning system is well vetted, well tested, that will only be relative to whatever environment it's seen before. So if a Fukushima like thing happens or something, then all of a sudden it's like, and as humans, we tend to be more trusting of a human in that scenario than a machine.
And whether it's right or not, that's a different question.
Yeah. Is that so? It sounds like the bulk of deployments of kind of AI in these operational contexts is in these, what you're calling, I think, open loop systems, where you're basically being suggestive to an operator. When that happens, are we also discovering a lot of peripheral use cases or things off to the side, a little bit of that operator where the machines are picking up and like not just getting us to the point where the humans were operating before, but maybe into a more enhanced place?
Yeah, augmentation. And I think the first part to get there is basically gaining trust. Whatever, like when we change the way we operate day to day, and there's like suddenly a computer that is, let's say, could replace you maybe in a far distant future, then of course the first thing is you're not really the person who will trust that system right away. There's like kind of like skepticism behind it. And of course that's dependent on where you are. Some countries have that more, some others have less of that. So that's the first step, like with taking easy use cases where you help an operator have their job, like to make their job easier. That's a good starting point, because if they see they can do their job better, get a better performance, that's the step when then you can suddenly introduce more and more parts where you can really help them and bring them up to the next level. But if you go to the, let's say, I tell you everything you're doing is wrong because this machine now is doing everything better than you as an operator, this will surely not fly, because then they will not accept the machine. They will actively do everything to not work with it.
Yeah, and to a large extent, this is like a user experience thing, right? Like, depending on how you present things, and
also even more so a change management thing, how you place it. And if you say, hey, this machine is there to help you do your job easier, make it better, and so on, it's probably a better placement. It's not just user experience of how you present it, it's just like how you place it in the cultural landscape.
So talk to us a little bit about the software landscape, that the systems that this operator is looking at. Like, who builds these kinds of systems? Can we think of these as like SaaS systems where there's evolution happening behind the scenes? Or is it custom built per plant?
Prepare to be zoomed back to the 1980s. So like almost all these systems. So first of all, for many reasons, you would not have the automation of such a plant in the cloud. Just first of all, for reliability and safety reasons. That's the first part, because you need to like have very strict guarantees in terms of interlocks, like when something goes wrong, that you can put the plant in a safe state. I don't think that's a good idea to do that offsite. That's the first step. The second part is these process control systems are built by specialized vendors like large companies, Siemens, and so on, that when you build these factories, you put them into place. You validate them, you run them. That's the entire operational technology part. It's completely custom made. The software that the operator is seeing is in most cases a graphical user interface that is very specialized to the purpose. It visualizes how the process looks like and shows you where all these sensors are. And that is, of course, a huge disconnect from basically what the process engineer sees, who sits with their machine in their office in that case. And even there, I'm not really aware if any of the flow sheet modeling tools are already available as a software as a service. Most of them are pieces of software that are installed in a machine. In some cases, you would add a backend on like a cluster or so on. Like when you think of similarly computational fluid dynamics software and something like this, where you develop on your machine and then you offload the computation into a cluster. But also there, I'm not aware that this on a large scale is done in the cloud, at least for the chemical engineering space.
And those capabilities, like you mentioned, Siemens building Is it more like Siemens building a toolkit that some engineers that work for a specific manufacturing plant would modify and configure to their purposes?
The operator will very likely not modify anything of that once it's put into place. It's basically pre-configured. You use it as like an appliance, I would almost say. It's put into place. And if like you want to do changes in there, like you want to change a sensor or so on, a maintenance crew from operational technology will change the sensor, will reconfigure the PID loops. It's a project to do something like this because everything has to be like made up to code, has to be compliant with ASHA and safety regulations and so on. You cannot just simply ship an update. Everything
so
has
it's
to be
actually
validated.
Like Siemens, like you buy an expensive package from Siemens and then they have some consulting folks that walk your plant and work with your people to configure it, something like that.
It could look like that. In some cases, you have internal experts that would perform updates on the let's say parameters and so on. But updating a process control system, I would say you do that in a maintenance interval every couple of years because it's a major thing that is ongoing. And just imagine if you have a factory that produces 5,000 tons of a material per day, and you sell this material for $500 a ton. That means $2.5 million every single day, meaning if your plant, due to a software error, does not run for one single day,
big problem.
You're losing 2.5 million. And so, sorry, I should have said that probably earlier. This is why the aversion to like go into anything that is not, let's say, I wouldn't call it bulletproof, but like really working is very, very high. Because just the risk of, let's say, that your machine locks up and doesn't work anymore is a huge risk.
So in that world, gaining incremental efficiency improvements via AI becomes a thing for the select few or something, the strong stomachs.
It's a tough cookie.
Let's see, fast forward for us like 10 years with everything you're seeing in the evolution in the, process, industrial, chemicals, manufacturing space, and everything you're seeing with the evolutions in machine learning and AI, like what does that intersection look like in 10 years?
I would say first thing is, I think similar to all other industries, I think in the next 10 years, we'll get to say our shit together when it comes to the integrations of legacy systems. That's the first thing. I'm pretty sure we'll get that dealt with. This like huge, let's say, access issue. One way or the other, we'll have to deal with it. The second part is that I believe with I would call it very painful learnings that are right now done in the field of autonomous driving, we'll probably get a way better idea of how to deal with AI in safety critical systems. The third part is that I believe the research that we're currently doing in terms of time series modeling will be so commonly applied to these issues that all these points that we currently cannot address, we can address at scale with stencils easily. You said earlier about like having reusable units and standard pre-trained models, and like you basically know what kind of type of model you need to take out of the cabinet in order to solve a time series problem like that. Right now, there is, to the best of my knowledge, no type of model structure that you could just pull out and say, hey, I have a time series problem. I want to forecast a time series. And by the way, I understand some parts of that physical system behind it. Here's, by the way, all the observations that I have, go. I believe here, with the research that is going on, in 10 years, we'll have quite a bit of software, quite a bit of understanding and model structures on how to do that.
Do you see a lot of activity in maybe the startup world addressing some of these problems? Who's innovating towards this 10-year future that you're seeing?
So I see some activities in universities that are working on from the chemical engineering world. There's a couple of groups working on this. In the field of time series modeling, I see some interest from the financial sector, because like all the data we're dealing with there is in many cases time series data.
Yeah, so I mean, there's an awful lot of people that are probably the best time series forecasters are all, predicting the stock market, so, like on some level.
And startup-wise, the thing is, the entry barrier that we talked about in the beginning is pretty high in this point. Like to get your foot into an industry that has a tradition of being very, let's say, strong in modeling, that is very strong in automation and has a culture of continuous improvement. I mean, there's all this Six Sigma and so on applied for many times. Plus, there are the legacy systems and this strong like disconnect between operating technology and information technology. These parts make it very difficult, I believe, for startups to enter into that space. Because for something like this, will you really get the funding that you need in order to hire this many people compared to like autonomous driving and so on? I'm not so sure. We said earlier, a lot of these things are already solved to a good state. However, I feel like there is one thing that could really change that, and that is if a strong push towards sustainability comes into play, and suddenly there's a huge innovation pressure that you really have to solve things that you previously couldn't solve. In that case, I could see that something is happening.
Well, let's talk a little bit about the sustainability tsunami or wave that's coming towards pretty much the entire economic world, right? Like, you've got everything from governmental entities, mandating, carbon accounting, if you will, to hedge funds, wanting to report on their companies and being able to understand their companies and their progress towards sustainability. A, what's the magnitude of that from where you sit? And B, how does that affect, this world that we've been discussing?
I'll ask a hypothetical question. Do you think people will still need toothpaste?
I'm pretty sure, yes.
And exactly that's the thing. Like, even though, like, if you look at the stock market, the traditional industries haven't been the, let's say, hottest child in terms of investments, you will still need a lot of these things. And even if we remove, let's say, all transportation fuels, meaning refinery and so on, the question is still, will we still need paint? Will we still need the liquid crystals for LCD displays? Will we still need, let's say, all the chemicals that we're using in our day-to-day products that we don't even think about?
Yes.
I would say very likely. So then the question is, then the question is, how do we produce them? So the question is like, how can we find new routes to produce a lot of the things and the performance materials we're seeing in day-to-day life in a different way? And that will likely mean that we have to think the entire value chain or the supply chain from raw materials into the goods we're using. And that creates, I believe, a huge pressure in terms of like, how can we do that? Because I'm not sure if we have answers, if we have the people there. And that's similar to many other things. That's a tsunami wave coming in.
Yeah.
If you really say we don't want to use any more oil, any more gas for like all the products that currently are produced by the chemical industry, I would say that's a huge challenge.
Yeah, I mean, there's many steps to it. I mean, I imagine like some of the earlier steps is just like, where does the power come from a plant that produces toothpaste or what all these materials you're talking about? That seems, like a good place to reduce
tangible. That's
your
the
footprint.
tangible.
Yeah, but you're kind of now talking about, well, okay, let's assume you've done that. That's sort of easy. Within our world, how do you start to source materials, in an efficient, in a carbon optimal manner, reduce carbon optimal manner? How do you get into your actual processes?
And let's spin a future. Let's say, think about the cyclical economy, that basically all the waste that you're producing, let's say you have a Ziploc bag, you've used this Ziploc bag. How can you reuse it? How can you also then, if you cannot directly reuse it, reuse the material to make something else? All of these parts, not completely clear, because probably use in a thermal way, meaning burning it to produce power, is probably not the smartest to do with this material.
Okay, I was gonna wrap up, but I still have more questions.
We can do a couple more minutes.
If you don't mind, we can do a couple more minutes, because like this environmental stuff, like I've had like a.
We can also do a follow-up on that one, like talk, have a couple of thoughts on, let's say, the sustainability big picture.
Yeah, I would love to do
that. Maybe to do that. No?
We didn't talk anything about Dataiku. Do you want to?
What I can say is right now is, let's say, when you have these whole points, and let's say you have your data all in a data infrastructure, and you want to do exactly these analysis, and you especially want to operate then such machine learning. So let's say from the heat exchanger we talked about previously.
Yes,
that's exactly what where platforms like Dataiku come into play. Like having the whole life cycle from model development, signing off, quality control, into deployment, and then monitoring both the data and the models in operation That's exactly where you are looking into platforms like this, when it's about governing them at scale, making sure that you have the risk in mind, and that you sit abstractly on the infrastructure. But we will surely not be the ones that deal with the process control system and interfacing. And there we would rely on partners, and we rely on partners actively.
Gotcha. Thanks a ton for coming on. This was super fun. I feel like I learned a lot about a lot of stuff I know very little about. So that was cool.
No worries. That was yeah. I also learned a couple of things, and also that's the important part when you do something like that and have a conversation. I'm also not the experts in all of these fields, so
yeah, no, that was fun.
Learning.
That is all for this episode of your AI Injection. As always, thank you so much for tuning in. If you enjoyed this episode on AI in chemical engineering and industrial processes, please feel free to tell your friends about us, give us a review, and check out our past episodes at podcast.xionics.com. That's podcast.xionics.com. And please also drop us a note if you've got a specific topic you'd like us to cover here.
That's all for this episode. I'm Deep Dillon, your host, saying check back soon for your next AI injection. In the meantime, if you need help injecting AI into your business, reach out to us at xionics.com. That's XYONIX.com. Whether it's text, audio, video, or other business data, we help all kinds of organizations like yours automatically find and operationalize transformative insights.